This is video 3 for lesson 4 on the combined gas law for unit 8 on gases. So we're going to look at our last two problems here, and you can pause at any time to try these and then I'll explain them. So number 3, we have a small research submarine with a volume of 120,000 liters and it has an internal pressure of 762 millimeters of mercury and a temperature of 68 degrees Fahrenheit. If the submarine descends to a depth where the pressure is 150 atmospheres and the temperature is 3.0 degrees Celsius, what will be the volume of the gas inside if the hull breaks? So this one is a little bit more tricky. So we have a volume of 120,000 liters, a pressure in millimeters of mercury, and a temperature in degrees Fahrenheit. The pressure is going to increase tremendously and the temperature is going to go down. So what will be the volume of the gas? So with this one, P1, V1, and T1. Pressure 1 is 762 millimeters of mercury. This one, P2, is in atmospheres. So I'm going to change this one to atmospheres. So 1 atmosphere is 760 millimeters of mercury. So 762 divided by 760 gives me 1.00 atmospheres. Pressure 2 is 150 atmospheres. The volume is 120,000 liters, and V2 we're looking for. Temperature 1 is 68 degrees Fahrenheit, so we have to change that to degrees Celsius. So degrees Celsius is equal to 5/9 times the degrees Fahrenheit minus 32. So 68 minus 32 equals times 5 divided by 9 gives me 20 degrees Celsius. Add 273 to that and I get 293 Kelvin. T2 is 3.0 degrees Celsius. I add 273 to that and I get 276 Kelvin. So now we have everything ready to put into our problem. P1 times V1 all over T1 equals P2 times V2 all over T2. And I apologize for not giving you enough room here. Looks like I have to write pretty small, but that's okay. So I have to divide both sides by 150 atmospheres and 298 Kelvin. So our kelvins and our atmospheres cross off. And let's see what happens to our volume. So 1.00 times 120,000 times 276 Kelvin divided by 150 atmospheres divided by 298 Kelvin gives us, and we should have two significant figures, so 740 liters. So we went from 120,000 liters to 740 liters. That is a huge, huge difference. Now our last problem. This one's kind of funny. People who are angry sometimes say that they feel like they're going to explode. If a calm person with a lung capacity of 3.5 liters and a body temperature of 37.2 degrees Celsius at standard pressure gets angry, what will be the volume of the lungs when the temperature rises to 39.0 degrees Celsius and the pressure increases to 765 millimeters of mercury? So we'll see if they explode. So here is our volume at body temperature and standard pressure. We want to know what the volume will be if the temperature is 39.0 degrees Celsius and our pressure is 765 millimeters of mercury. So pressure 1 with standard pressure. Well, that's 1.00 atmospheres. And if we look on our conversion chart, 1 atmosphere is 760 millimeters of mercury. That makes it easy because our pressure 2 is given in millimeters of mercury already. Volume 1 is 3.50 liters. We want to know what the new volume will be. 37.2 degrees Celsius is our initial temperature, and 39.0 degrees Celsius is our new temperature. So add 273 to both of those. (310.2 Kelvin). And 312.0 Kelvin. So we have everything we need. So pressure 1 times volume 1 all over temperature 1 is equal to P2 times V2, which is our unknown, all over 312.0 Kelvin. So to give me a little bit more space, I'm going to write out the cross multiply down here. 760 millimeters of mercury times 3.50 liters times 312.0 Kelvin is equal to 765 millimeters of mercury times V2 times our 310.2 Kelvin. So we have to get V2 by itself. So I'm going to divide both sides by 765 millimeters of mercury and 310.2 Kelvin. That crosses them out on this side, crosses out units on this side. We're left with V2, and now we just have to put this in a calculator. 760 times 3.5 times 312.0, it equals, divided by the quantity, 765 times 310.2, Bose quantity. And we get, well, let's see how many significant figures we need. It looks like we have 3, and it ends up being the same with significant figures. So no, an angry person is not going to explode. Their volume basically stays exactly the same. So no explosion.